How's everyone? Looking forward to the break? Mm-hmm. So do I. Okay. Hopefully I'll give you something that it's not too bad to digest. Okay, so you can afterwards handle the turkey. Okay, so we are talking about integer programming, and last time, not with very nice timing, we started the problem and we could not finish it, so we'll have to do that. So let's pick up the problem from last time. So I'll just state it here. So the example we did was minimizing subject to okay. So that was the problem we took last time. Can everyone see it? Is it covered by the screen? Is that okay to see? Yeah. Okay, so what we did last time was we solved it with the LP assistant normally, and we found the optimal solution, neglecting the integral constraint, and we found out that they were not integral. They were points with fractional parts. So we pick one of the equations in the final tableau with a fractional constant term on the right-hand side, and with some arguing, we put a new constraint on it. Is that right? So let me repeat. So for this one, I found out the z-min for this problem was, what was that? Well, that doesn't really matter, but it's obtained at 0, 15/4, and then there are slack variables I'm not taking. So in the final tableau, what we did, we wrote out that equation with the fractional terms, and we broke the coefficient into the integer part plus the fractional part. Remember doing that? And then we rearranged terms, moving all the integer terms to one side of the equation. And then we conclude that the left-hand side with the fractional part must be an integer value in the end, right? And that gave us the additional constraint. So let's put that up so everybody remembers how that additional constraint was formed. Okay, we'll look more into that today. So that one gives me negative 1/2 x1 minus 1/4 x3 plus x5 equals negative 3/4. Okay, so the next thing to do would be putting this into the final tableau as a new constraint and solve the problem with 3 constraints now, right? And in the hope that it will put the answer into the integer form. So what I will do today will be I will go to LP assistance and show you how this can be done. Is that okay? Because later you have homework. You really need to know what to do. So let's say, start from the beginning. I am given the original problem, and I'm going to put it into LP assistant. And you know you will have to add 2 slack variables, which will give me 4 variables. Let's punch in the numbers. 1, is that right? Negative 1, and that's a slack variable. And the right-hand side is 2. And then the second equation was 2, 4, 1, and the right-hand side was 15, and the objective function, negative 3. And then I need to specify my basic variable will be x3 and x4. Is it clear? That we have done many times. We are professionals, all right? Okay, so you can use regular simplex method. This is negative, and I click on the 4 to pivot, and I find the answer, but the answers are not integral. So this table, actually we had it on the blackboard last time. We just wrote it down by hand. Okay. Now you see it's in the LP assistant, and now I need to add that new constraint that we just wrote down on the board onto the final tableau here, okay? So in the LP assistant, there is a very useful feature. If you go to problem, you can form a new problem from the one you have just done. If you choose that, what it will do would be it copy the final tableau there and give you as the starting point for your new problem. Is that clear? That is very useful. So you click that, then you have the final tableau. And now you need to go to edit, because now I need to add a new constraint and a new variable, because I added another slack variable. So let's do that. Add a constraint, add a regular variable. So, okay, so let's put in that final constraint that we came up with. So for x1, I think I wrote something wrong. I think this is x4. Was it x4 that we came up last time? Let me check my notes again. Yeah, it's x4. So sorry, I copied it wrong. So x1 is 1.5, x2, x3, 0, x4. Wait a second. Wait a second. I need to make them all negative. So the final one is negative. Wait a second. Negative 1/2, 0, 0, and this will be negative 1/4, and that's 1, and the final is negative 3/4. Is that right? Okay, so that is the new constraint that we put in, and then I see that x5 can be chosen as the basic variable here. Is it clear? Right, now we have to go and pivot. Now you have to be careful. So what you will be using here will be the dual simplex. So you have to switch the algorithm to the dual simplex. And then we look at the B, we see that is a negative one, so this row will be chosen, and then I will look at the ratio of the negative coefficients. This gives me negative 3, this gives me negative 5. Which one should I pick? The one that's bigger in real value, right? So I will be clicking right here, and some miracle happened, everything turned integer. That constraint we added now turned everything into integer. Now you see your optimal, so now this is all positive, this is all positive, and you know that's the optimal solution. Is that right? That's the optimal minimum value, and this is the optimal solution point. Is that clear? How this is being done, how to copy the final tableau and start a new problem and then adding new constraints. Okay? So with all that, so let's go back to the blackboard. We'll have more examples, so don't worry. Where's my chalk? I lost it. So we see, now we are lucky, so I write now solve with LP assistant. I get the following. One step, I get the answer. The minimum value of z now is negative 9, attained at, what is at? x1 is 0, x2, 3, x3, 5, and x4 is 3, and x5, 0. But the last three variables are all slack variable, not of importance is the x1 and x2. They are the original variables. So let me block them. So is it clear how this is being carried out? Okay. So procedurally speaking, let's hope this is clear. And what I want to do next will be to give an explanation of what is happening here. What does this constraint do to my problem? So this is a problem chosen on purpose to have only two variables, so we can illustrate everything on a graph. Okay, so let's see what happens to the graph. So a geometric explanation of what's happening. Okay. So let's plot the feasible region. Okay, so the feasible region of the original problem, if I shall be able to plot x1, x2, this is a bit hard, so 1, 2, 3, 4, 1, 2, 3, 4. Those are my grid points. Okay, so if you draw the constraint, you draw the line with the equal sign, then you have two lines, and you check which side is feasible, and you can form the feasible region. Are we all okay doing that? So I will just show you what will come out of this drawing. So one would go like this, and the other would go like this. Okay, so and then that's the feasible region under. And when you solve the original problem without the integral constraint, you find out that this was the optimal solution at 0. Let's write it out. This is 0, 15 over 4, 3 3/4. Is that right? That was the optimal solution without putting the integral constraint. So now let's check what is this constraint doing. The constraint, the new constraint, let's check. Let me do it this side. The constraint. So what is the constraint? So you know that x5 is actually some kind of a slack variable for this. You can write it into an inequality. So I will have in half x1 plus a fourth x4 bigger than 3 over 4. Right? That is actually the new constraint we put in. Okay? And I want to rewrite this in terms of the original variable, x1 and x2. I can easily replace x4. x4 is nothing but the slack variable, so I can use this relation. x4 will be 15 minus 2x1 minus 4x2. I can plug that in. Is that right? So let's do that computation in detail. Then I have and half x1 plus a fourth. Copy this. Bigger than 3 over 4. So all I did is plug in the expression for x4. And then let's see, collect like terms, and half x1, this will give me negative half x1, so they actually cancel each other. And then I will have 15, let's distribute 1/4 here. And if I multiply that, I get negative x2 bigger than 3 over 4. Is that right? So I can move the constant. Now let's say move x2 over, and this over here, 15 minus 3 is 12, 12 over 4 is 3. So this simply gives me x2 less than 3. That's the new constraint, basically. Even though it takes this fancy form right here, in the core it's telling you that is what's being added, right? We agree? So let's see what is that constraint. Let's draw with red. So that's 3. So the old feasible region is here. Let me remove these lines so you see clearly. That's the feasible region. And now I have a new constraint. It says x2 must be less than equal 3. So I draw a line, it equals 3, and then the feasible region is below. Is that right? So what does that do? You see that the old optimal solution is now not feasible. It's being cut out. Now the feasible region, this lies outside, the feasible region becomes smaller. Is that right? I'm cutting off one little piece. And where I cut is along the grid where I have integer values, right? So after this cutting, you see we solved the new problem, and I found the optimal solution at 0, 3. That means the optimal solution after the cutting moved from this point down to this point. That becomes the optimal solution, 0, 3, after cutting off one piece. Is that clear what it's doing? So this process carries the name of cutting plane. That's why we call it. So now you see what it means. Basically, I find the old optimal solution, which is not integral. I find a way of cutting it off my feasible region in a way that hopefully after my cutting, the new optimal solution would be on an integer grid point or partially. If it still doesn't, then I keep cutting until this happens. Is that clear what this is doing? Any questions? Okay. Now let's talk about the general algorithm, because this is just an example. Okay. So I think the whole approach is clear for us, right? We solve it without thinking the integral constraint by LP assistant, and we find the solution. If it's not integral, we perform this cutting, new constraint, and then we solve it again. Okay, so what I will be putting up as the part of the integral in the algorithm will be exactly how do you add a new constraint, meaning how do you cut, adding new constraint. Exactly that part we're going to summarize and write it out. So, okay, so what we did, recalled what we did. We looked at the final tableau and we checked the B and we select one row where B is not integer. Is that right? So that's your starting point. I will select a row in the final tableau. Okay, let's just call F, where the BI is not integer. Any of them you can choose. You can choose the one with the largest integer part, but it doesn't really matter. And then we write out this equation from the final tableau. Okay, let's say this equation is the following. Summing over A, I, J, X, J, that's the left-hand side, sum over all the J's, and then equal the right-hand side, BI. Is that okay? Okay, so let's say that equation is important because I'm going to form a new constraint out of it. Okay, so apologize in advance, there'll be a bit annoying notation, but hopefully the algorithm is clear. I just have to write it with some notation. So you know what we did was breaking up all the coefficients into an integer part and a fractional part. Then I need to introduce some notation for those. Is that okay? So I will use this notation now. Denote, if I give any number A and I put a bracket around it, that means this will be the integer part of A. Okay? And then if you take out the integer part of A, then if I do A minus A bracket, what remains will be the fractional part. Is that right? Okay, so here is something a little bit tricky. So the fractional part, in this notation here, is always positive, okay, which lies on the interval from 0 to 1, not containing 1. Is that clear? I'll give examples. So, for example, if I just take some silly example, let's say A equals 3.5. What will be the integer part of A? Oh, it's 3. Is that right? Simply taking that. And what will be the fractional part of A? Well, it's 3.5 minus 3, which is 0.5. So for positive number, it's clear. What if I have a negative number? Let's say negative 2.4. What will be the integer part of A so that the fractional part will be between 0 and 1? I need to take the integer value that's less than A. Is that right? Which will be negative 3, right? So be careful here, okay? Negative 3. And then the A minus A, the fractional part, will be negative 2.4 minus negative 3, which will be 0.6. Is that clear? So let me put a star here. Be careful when it's negative. That's what you have to do, all right? The fractional part is always positive. Okay, introduce a few more notations. So now in my problem, I have coefficients A, and I have the right-hand side B, and this is a bit annoying to write the fractional part, so let me denote something. So let's call this F to be the fractional part. Fij will simply equal Aij minus Aij, the fractional part of the A coefficients. Okay, this is F with double index, and F with single index will be the fractional part on the right hand side, so it will be Bi minus integer part of Bi. So now you know all these F's, they are non-negative. They take value between 0 and 1. Okay? Okay, so with all that, I'm going to rewrite the equation star. Now star becomes the following. Okay, I break it up. So I have summation over J. I have, so any number is written as the sum of its integer part and its fractional part. Is that right? So xj, and the right hand side is the integer part plus its fractional part. Okay. And then we do the same thing. We keep the fractional part on the left and move all the integer parts to the right. Okay, so rearrange. Fractional parts on the left, so I have summation over Fij xj, and then I take this fractional part over Fi, and then move everything integer to the right hand side. Remember doing that for the first example? Okay, so here comes the key argument. All these are integer numbers. It has to give me, in the end, an integer number. Is that right? And then the left-hand side equals that, and it must be an integer as well. So what is the smallest value this integer can take? Well, you know xj's are bigger than 0. The smallest value all these xj's can take are 0. So the smallest value this whole thing can take will be negative fi, which is a fractional number between 0 and 1. Is that right? But it cannot take that value because the whole thing has to be an integer. So the smallest integer this can have is somewhat bigger than that one, right? Will be exactly 0. Is that clear, that argument? So smallest integer value of the left-hand side is 0. So left-hand side is integer and smallest value is 0, so it has to be a non-negative integer. And we call that a new variable, and that becomes the new constraint. Okay? So we let left-hand side equal to a new variable, xn plus 1. Okay? And that gives me the new constraint. So the new constraint is the following. Okay, it's basically the left-hand side equal xm plus 1. I'm just going to rearrange terms. I will move the constant term to the right-hand side, so this will be ready to go into the tableau. All right? And I also want xm plus 1 to serve as a basic variable, so I want the coefficient to be 1 right there. Okay, so if you just rearrange a bit the term, I have the following: negative summation over j fi j xj plus xm plus 1 equals negative fractional part from the right-hand side. So let me block this. So all this discussion in the end leads to this choice of the new constraint. Looking at this and see what it says. It says your new constraint will be that row in the final tableau, and you go through each element of A and you take out its fractional part and make it negative times that x, right? Add them all up, and then you have a new variable which will have coefficient 1. And then the right-hand side, the constant term will be that constant term, the row you choose, the fractional part, but make it negative. So we can actually write down the constraint immediately following this formula. Is that clear? We'll take it in an example, all right? Okay, so let's take another example just to see. There will be homework problems like that, and this will show you how you have to work everything out. Is this position okay? I put everything here. Okay? So let's take an example. Minimizing x1 minus 2 x2 subject to Okay, so we will go through step by step and see how this problem can be solved. Okay, so step 1, well, I take this problem, I make it into a standard form, canonical form, I send it in to solve it with the LP assistant. So you should work with the LP Assistant open right next to you. So let's go to that. So with all that helping, it should actually be quite okay. Let's just remove this and rewrite the problem into LP Assistant. All right. So I have 2 and 1, 0, 0, 5. And the second row would be negative 4, 4, 0, 1, and 5. And the objective function, there's a negative 2, 0, 0. Is that right? All right, so how do I solve it? I have a negative 2 here. I need to pivot. I need to check the ratio. That's 1.2. That's 5. I choose the small one. I pivot there. Then I have a negative 1 still, and I have a positive 3, and I pivot over there. And okay, now these are all positive, so I am done. That's the optimal solution. Is that clear? We should be professionals with this. This is such a very simple example. Okay, so I solved it. Let's see. I find the optimal solution at the point 5 over 4 and 5 over 2 for x1 and x2. Let me just record that. But they are not integers, so that's no good. Now I need to pick one of them to continue. Let's look at the first row. The fractional part is 1/4. The second one, the fractional part is 1/2. That's bigger, right? So I'm going to pick the second row. Okay, let's just follow the algorithm. So pick the second row. Okay, and you need to add a new constraint. So you can write out the new constraint right away following that formula we put there. So let me make the table a bit lower so I can point at it what I will be picking. Whoops, that's too low. Okay. So if I take the second tableau, a second row in the tableau I want, so the integer part of this is 0, integer part of this is 0, integer part of this is 1/3, and that one I take, right? I need to make that negative, so I have negative 1/3 is in front of x3. Is that right? And then integer part of this is 1/6 is in front of x4, so negative 1/6 x4. Is that right? Now I need to add the new variable x5. Okay? And then the right hand side, I have 5 over 2. What's the integer part of it? Is half. Is that right? Take half. But I have to make it negative. Is it clear? You can write this out just like that. That will be your new constraint. Okay? And then once you form that, I will add it, and then I will put it into solve again with the LP Assistant. So let's go to LP Assistant and see what it tells me. Okay, so make sure this is the thing you are selected, and you go to problem, and you say new from that, and it will copy the final tableau for you. Okay, and then you go about and add it, and to add a new constraint. So add a constraint and add a variable. So what's the new constraint here? Is 0, 0. This is negative 1 over 3. That's negative 1 over 6. And that's 1. And the right hand side is negative 1 over 2. Is it clear? And then I collect, set the basic variable x5. Is okay? Any question? So now pivot. So what method should I use? Simplex or dual simplex?
What's the reason behind picking the second row as the new
Oh, it's because the fractional part is bigger, but it doesn't matter. You can pick the first one. But if you want a deterministic algorithm that I have a choice, which one do I choose? Okay, I choose the big one. Then you can do that. All right? It doesn't matter. All right, so my question, should I use simplex or dual simplex for this problem? The dual, yeah. All right, so this is negative. Let's choose between these two candidates. That's -1, -2.5. I have to choose here. Is that right? I click on that. Okay, now after one pivot, I see that I have right-hand side all positive now. So this is the new optimal solution, and that's the new optimal value for this problem with this new constraint, right? So let's collect that. So that tells me the following. So this gives me the new optimal solution, which is 3/4. I'm only recording x1 and x2, all right, and 2. But then I see it's still fractional. It's still no good. I need to continue. What do I do? Step 4. Okay, so I have two constants on the right-hand side that are fractional. You see, it did manage to make this an integer, didn't it, right? So we feel optimistic, okay? It's going towards where it needs to go. Now I need to choose between the first row and the last. Which one has a bigger fractional part? The first one, right? Let's pick that. It doesn't really matter. You can pick the last. So pick the first row. And then I form my second new constraint. I keep adding more constraints to it. So will we be able to write it out directly? What will be the first non-zero term? Will I have x1, x2, x3? I will have x4, which is a fraction number, right? So what would I have? Be a bit careful here. -1/4. How do I break this into an integer plus a positive fraction? This will be, the integer part will be -2, right? And the fractional part will be 3/4. Okay? So be careful. That is something I can see that could trick everyone in the exam. You're so confused, you just put -1/4 there, which is wrong.
Should be
-1. Of course. But the fractional part is 3/4. I got that right. So the continuation would be correct. Okay, so I will take the negative of that. So my new constraint will be 3/4. Where is that? That is in front of x4. And then nothing else. Is that right? And I'll be adding a new variable, x6. And then the right-hand side is 4/3, and the fractional part is 4/3. But I have to make it negative. Is that okay? That's the new constraint. Okay, let's put that in and see what we get. So you go to the tableau that you had, you just did with already one constraint added on top of it, and you click problem and you form a new problem based on that one. Is that clear? And then it takes that final tableau and give it to you. So you can start. So I have to go and edit. I need to add a new constraint, add a new variable. Is it okay? All right, let's add that constraint. The constraint we have formed will be in front of x4. I have -3/4, and then x6, I have 1. The right-hand side, -3/4. Okay, and then I see that y6 is a nice basic variable I can use. Okay, and then we can pivot. Is it clear? So let's pivot. So of course that's the one being chosen because it has negative, and there's only one negative number. I'll click on it. Look, everything becomes integer now. Your solution and the optimal value. Okay, so let's write this down. We are lucky. Now we're done. So where? I keep losing all those chalks. Where do I put you? Over here. Okay. I solve again with the LP assistant, and it gives me the final solution. So Z min equals -3 at, if I only record x1 and x2, is at 1 and 2. Okay, the others are slack variables. Is it okay how this is being done? Would you be able to do similar things in your homework? There'll be a couple of problems that you have to turn on the LP assistant next to you and put it in the number and run it and find the answer and then record it as I did here. But you also have to collect the tableau from the LP assistant as part of your answer. Is that clear? Right. Is that feasible? So in the end, what you record is not that much, but there's quite a bit of work over there to click and type in the numbers, all right? Okay, let's get that off. I will not use it for a while, maybe not at all, we'll see. All right, so what I want to do next would be, as I did for the first example, I would like to offer a graphic explanation of what's happening, in particular by adding these two constraints. Let's call this constraint C1, and then that's the constraint C2. What actually did they do to the feasible region? Is that okay? So, and graphic explanation. I think you shall be able to do it. You can do together and see if you get the same thing. All right. The test of graphic. Okay, talking about feasible regions. So let's try to sketch the feasible region. X1, X2. Let's say 1, 2, 1, 2. Okay, I need to draw the line for this with the equal sign and the line for this with the equal sign and form the feasible region. So let's say if I do that for the second equation, for the first, this should be, if I mark the grid points of this not perfect coordinate that I did. So this has to be slope 1. That's something going on like that. And there's another one going up. Like this. Okay, pretend they're straight lines. Those. So this one is the one that's -4x1 plus 4x2 equals 5 with slope 1, and this is the one, the other equation, 2x1 plus x2 equals 5. And the feasible region is below this quadrilateral shape. And then when we solved the first step, we found out that that was the optimal solution right there. So that was the optimal solution with the coordinate 5/4, 5/2, which is not integral, so it's no good, right? Okay, now let's check the constraints we put. Let's look at the first constraint. C1. What is that constraint actually? So C1 says negative 1/3 x3 minus negative 1/4 x4 shall be less than that. Let's get rid of the negative sign and write with positive sign. And is bigger than half. That's basically what it says, right? The x5 is a slack variable. Okay, let's put in the expression for x3. x3 is the slack variable of the first, so it's 5 minus 2x1 minus x2. And x4 is the slack for the second, which is 5 plus 4 x1 4 x2, and that shall be bigger than half. Okay. Can I skip the step collecting like terms and simple it out? You can do that. One step of work, you will find out this simply gives you x2 less than 2. Okay, so go back to the graph. So what does it do? x2 shall be less than equal to 2. Okay, so equal to is this line, so meaning I will cut right here, and this part is not feasible anymore. And that was actually where the old optimal solution was. You always have to cut like that, otherwise you don't get new optimal solutions. Is that right? So then after cutting, and I find out the optimal solution after cutting is 3/4, 2, which is exactly this corner here. So the optimal solution is moving down to this point, which is 3/4, 2. Is that right? 3/4 and 2. So it kind of make the x2 coordinate integral, but x1 is still a fraction number. Now let's look at our second cut with the constraint C2. Let's do it with green and see what it does. So what is C2? Well, C2 basically says 3/4 x4 shall be bigger than equal to 3/4. Is that right? This is basically x4 bigger than 1. Plug in the expression for x4. I have 5 plus 4x1 minus 4x2 bigger than 1. And moving the 5 over, you get -4. Get rid of 4. You get a simple expression, x1 minus x2 bigger than -1. Is that right? Let's draw that line and figure that out. So that one goes through the point. If you put equal sign 0, 1, it goes through, and also 1, 2, it goes through. So it cuts right here. Is that clear? So that second old optimal point from the previous step is now not feasible. It's cut it outside. So you have to look for a new one, and then you see that the new one, the new optimal solution is actually here. So it's moving to here. So this is with the 1 and 2. So now it's at a grid point. It's integral, and that is your solution. Is it clear how this cutting plane is working? So this example shows that the cutting does not necessarily have to be parallel to the axis, all right? You could be cutting with the lines with slopes, okay? But after cutting, the hope is the new vertices should take as many integer coordinates as possible. In the end, it's all integer, then you're done. Is it okay? Any questions? I think you will have quite a few of these to practice on in your homework, okay? Right. If you have no questions, then I will move on and give an introduction to the next method. I don't know how much I will be able to cover, but let's try. So 6.4, this is called a branch and bound algorithm. Okay, so let me give some brief introduction, but actually it's very hard to say all these with words. So you have a integer programming problem that's given to you, and what you do as the first step, always you solve this as a linear programming problem with simplex method, right? Meaning neglect integral constraint. So you see the simplex method will be used over and over, and then you check the answer if the optimal solution, if you're so lucky that first try it's already integral, and then you're done. Nothing else. Okay? That's usually, it doesn't happen. And then you need to introduce something new if it is otherwise, meaning I do not have an integer optimal solution. So here the way of thinking is a little bit similar to the cutting plane in some sense, meaning now I will introduce new problems that will have additional constraints, but given in a specific way. Okay, so now I will create actually two new problems, and they will be very important. They'll be distinct. Okay, let me underline that. I will make two new problems. They're distinct, meaning their feasible regions do not overlap at all. Okay, it's disjoint. Okay. So for each one by adding a new constraint. Okay, from the original problem. And then I solve them, and then there will be a lot of discussion. Depending on the answer comes out, you have to analyze the situation and probably split further and further until you find the solution. Okay, so let's do it through an example. So through the example. Through an example. How about I will just take this same example as the last one. An example will work. It's to illustrate the idea. So I'll be just taking this example. Is that okay? So the last example. Okay, I'll show you how it can be done using a different algorithm. Okay, so this example, I will have to do quite a bit of work. So let's call these levels. So level 1, the first level, I solve it, solve the problem with the LP assistant, meaning neglecting the integral constraint, and I find the solution. Okay, so the solution, they are here, and I did not record the z, the minimum value of z, but it was on the tableau. We could write out. So let me erase this. So I need the space here to talk about more things. So in the tableau we had all those numbers. So I solved this. So let me draw this graph here. So level 1, I record the solution in this box. So the solution gives me the minimum value of z is negative 3/4 at x1 was 1 1/4, and x2 is 2.5. That's what I got by solving it. Okay? So what information does it give me? Well, I see it's not integral, it's not optimal. For my integer programming, I need to do some more, but it gives me some information. It says, neglecting the integral constraint, the minimum now is negative 3 something. What does it say to the minimum if you have the integral constraint? What can you say? This gives me some information. I know the final minimum. Do you think the final minimum will be, let's say, negative 4? Would that be possible? You understand what I'm asking? This one tells you, without restricting to grid points, that's the minimum. And then if you restrict to the grid point, you are considering a smaller set. Your minimum will be possibly bigger than that. Is that right? And the minimum takes integer values, right? We're talking about pure integer programming. So which means the minimum has to be bigger than negative 3. Does that make sense? So the actual minimum, this one gives me that piece of information. Okay, keep that in the hand. Now I form my level 2. What do I do? Well, I will put up new constraints, and I form 2 new problems. So what will be the constraints that I put? I randomly pick any of the variables that does not have an integer solution. Let's say I pick x1, just random. I could pick x2, it doesn't matter. And then I see x1 lies between 1 and 2. Those are the 2 nearby integer for that answer. Is that right? So I will form 2 new constraints by exactly going around that. So one would be x1 shall be less than 1. The other will be x1 shall be bigger than 2, which will not include the x1 right there. One is on the left, one is on the right. That x1 is in the middle. It doesn't belong to any of these 2 new constraints. Is that clear? And then I form 2 problems. Okay? So this will be, say, x1 less than 1 goes this way, x1 bigger than 2. So this will be my level 2. Let's say that's the problem 2a. I always split into 2 problems. All right? And that's my problem 2b. I will open it here. Okay, so form problem 2a and 2b. Okay, and I can solve them, right? Solve them with the LP assistant. Okay, so there's a lot to do here. So let's say I solve this. This gives me z min is negative 3.5, and x1 is 1, x2 is 2 1/4. And then for the other one, if I solve it, I get z min equals 0. x1 is 2, x2 is 1. Okay. So what do they tell me? Let's check the answer for 2a. I see that the answer is not integral, right? it's giving me this z min, which is negative 3.5, and I see that this minimum, it's bigger than that, but it's less than this mean, so that can't be. Of course it can't be, it's not good enough, right? So I see that this is bigger than even the first one, negative 3/4, and it's still less than that. So this will not be the optimal. And what about 2b, the answer there, what does it tell me? And I see for this answer, everything is integral, right? That's an integer, the final answer is integer. So I found out that in the feasible region, there is a point with integral coordinate that gives me value 0. But I don't know if it's optimal or not. Is that right? But I know that it can take value 0 at some point. So what does it tell me? So let me see. So first I say these answers are all integral, and then I observe that z equals 0 at this point 2 and 1. If z takes value 0 at some given point, then I know the minimum shall be less than that. Is that right? Because it can get 0. It might be even less than 0. If it's bigger than 0, that's not my minimum. Does that make sense? So now I know the minimum value, this gives me this information. The minimum value will be less than 0. Collecting what I had from the first step, it shall be bigger than negative 3. So I nail down now. I'm looking for a minimum between negative 3 and 0. Does that make sense? Okay, it's quite a bit of information to collect and to think. Okay, and then, okay, so it doesn't make sense to break this up into further. They're already all integer. So now I make a choice that I will choose 2a, and I will further make more branches and do my analysis. Okay, so here's you reach the conclusion. Choose problem 2a to work further. All right, so now I form a level 3. Starting with problem 2a, I will add a set of constraints that are disjoint, that will not include the optimal solution here in it. So x2 is the one that has the fractional thing. And so I will pick that one. So my constraint will be choosing x2 less than 2. So this one doesn't satisfy. And the other one, x2 bigger than 3. So this does not satisfy that constraint. Is that clear? What I'm doing every time you add the constraint is around this fractional number, you have two nearby integers, and you take the left of the smaller one and the right of the bigger one. So it does not include that number. Okay? So now I have level 3a. That is, let's say, x2 less than 2, and this is x2 bigger than 3. So that's totally disjoint. So this is level 3, problem B, and then I will solve it. I will solve these two problems with LP Assistant again, and I will record my answer. Okay, so let me erase something. Quite labor intensive, isn't it? If you don't have the LP Assistant, you have to do everything by hand. Not so pleasant, huh? Okay, next time we will have an example that we actually go through the LP Assistant and all the detail. Okay, let's see. Solve. So use that. So I form problem 3a and 3b. Okay, and then you can solve. just by adding one more constraint, you can solve it. Let's say 3a gives me the answer. I solved it, and I record my answer here. Z mean negative 3 1/4. X1 is 3/4. X2 is 2. And then for this constraint, and I found out that is not feasible, because it completely cuts out the whole feasible region. There's nothing left there. So that's not feasible. Okay. So if that is the case, okay, so let's look at answer 3a. This is not integral. And then I have the minimum solution, which is negative 3 and 1/4. And I know my final answer has to be between negative 3 and 0. That's not there, right? And 3b is not feasible. I cannot continue from here. So I will choose 3a to continue. Is that clear? Now I break it up into 2 more. Now I have the level 4. Okay, start from 3a. I look at one of the solutions that is not integer, so pick x1. And the 2 nearby integer around that is 0 and 1. So the 2 constraint would be x1 is less than equal 0, which means it can only take value 0 because it cannot be less than 0, right? That's the constraint. Or the other one will be x1 is bigger than 1. Is that clear? You cannot go negative. It will be less than 0. Okay, so that gives me the level 4 for A, let's say, and that's for B. So for A is additional constraint, x1 is 0. And here is x1 is bigger than 1. Okay? I have 2 problems. I send it in to LP Assistant, and then I solve them. Okay? So I form 4A and 4B. Is that clear? So 4A, I added x1 is 0. 4B, I added x1 is bigger than 1. Okay? So if you solve that, for 4a, I have the solution z min is negative 2.5, x1 is 0, x2 is 5/4. And then for 4b, I have z min is negative 3, and x1 is 1, x2 is 2. Okay. What can I say now? Let's look at these 2 answers. So I solved them. Okay, so what does 4a tells me? 4a tells me it finds an optimal value negative 2.5, and the coordinate is not integral, right? So this value lies between negative 3 and 0 as we expect it to be. It has to be there, some value there. And that's not optimal, so we know that because it's not even integral. So 4a is not integral. That's no good. And what do you say about the solution in 4b? They're all integers, is that right? So I see that I have found a solution that is everything is an integer, and I found out that the minimum value at that integer solution is negative 3. Do you think that's the optimal? Do you want to comment? What observation we have made over here? The final optimal value should lie between -3, and 0. I found one point, it takes value -3. That's the optimal point because it cannot be lower than that. Is that clear? So you conclude that this is the final optimal value. Okay, so that's attained at x1 is 1 and x2 equals 2. Is that clear? Question? Yeah?
What's the x2 value in the lower left?
Oh, 5/4?
5.
Yeah. No. Any questions? So is it clear at least what I did for this example? If you don't see a general algorithm yet, and we'll talk about that. Is it clear what I did in this example? You break the constraint, pick an answer that is not an integer, and you form two constraints that does not include that answer in it, right? That's excluded. So you'll be seeking new solutions in both of these problems, right? But that's not all, because every time LP Assistant spit out some answer to you, you have to look at it and you have to analyze, as we did here. You see, we made that conclusion here, which is important. And then we made this conclusion at that step, which nailed down what we have to look for, right? And that made us say that right here, I stop, because that's it, that's the optimal. Is that clear? So this really involves a lot, okay? And it takes many, many, many steps. And we'll not even talk about the convergence of this algorithm. It's an algorithm. Is that okay? Okay, so next time we'll talk a general approach, probably we already know, and we'll take another example. We'll open LP Assistance and go through it. All right? Okay. So have a